Two questions for homework last night, page 491, number 1 and 2. I already had a request to go over both of them, so we'll do that, starting with question number 1. One says, 97-kilogram hockey center stops momentarily in front of the net. He's checked from the side by 104-kilogram defenseman skating to the east, bounces off at south of east. What's the velocity of the defenseman immediately after the check? The context of the question, I think everybody gets. Okay, there's, you might not be a hockey fan, but you know that you can picture, a guy standing in front of the net, or a guy skating to the front of the net, stopping and then getting hit, okay, and bouncing off in a certain direction. There's a couple of things here, though, that we've kind of got to take note of and kind of got to be able to use our reading skills to kind of catch, right? The first thing is the fact that the hockey center stops. That infers that he was moving. He was moving before this problem began. Does that matter? No, of course not. The problem is the collision. If he was moving before it began, or if he wasn't, it doesn't make any difference. So let's just say he's already stopped. Okay, the second thing, and I think probably the bigger thing that leads to confusion in this question, is this. He is checked from the side by this and bounces off at 0.940. There's a lot of people that read that and say, okay, which guy bounced off? Was it guy number 1 or was it guy number 2? He did, exactly, he did. It's the 97-kilogram center, okay? The 97-kilogram center is checked, and he bounces off at 0.940. So if we're going to call the center object number 1, then the final velocity of object number 1 is going to be 0.940 at 18 degrees. That make sense? Okay. I mean, obviously, that's important that we get that right. That's a matter of reading through that, right? We've got to read through that and understand who it is that has that final velocity. I saw a picture of it here. The 97-kilogram center, let's say that he's object number 1, 97.0 kilograms. He's moving at 0 meters per second. He's checked by object number 2 going to the east at 1.82 meters per second, and he has a mass, of course, of 104 kilograms. Now, you guys know this, right? If you want to make object number 1 bounce down here at 18.5 degrees south of east, then you got to hit him on this side, right? Okay, direct him over here. But if you do that, you guys also know intuitively, probably, that you're going to go up here somewhere. Okay, if you're object number 2, you're going to bounce up here somewhere. We want to find out how fast you're moving when you bounce up there. Okay, we want to find out your velocity, including a direction. All right, 5 words. 5 words should come to mind as soon as we see this picture. What are they? I don't like funny angles. Okay, I don't like funny angles, so let's get rid of it. Okay, let's take the 18.5. Let's do a little thing down here. You could do it right on this diagram. I don't like to do that just because I find the diagram gets a little cluttered if I start drawing more lines that are already on there. So I like to make it a separate diagram here. 18.5 degrees, 0.940. This is going to be x, this is going to be y. Okay, let's get the value of x and y here. Which side of the triangle there is our x side? Opposite, adjacent, or hypotenuse? It's adjacent. So which trig function are we going to use along with adjacent and hypotenuse? Cosine, right. Let's say cosine 18.5 degrees is equal to adjacent over the hypotenuse, 0.940. Anybody have that value of x? 0.8914 meters per second. Thank you. Now let's find the y component. It's obviously going to be sine because it's the opposite side. Make sure your calculator's in degree mode, right? Okay, you're going to have a unit test. I almost forgot to mention this. Unit test next Wednesday, so a week from yesterday. We're going to clear your calculators for your unit test. It will go back to radian mode. Okay, when you get your calculator cleared. Okay, so make sure you switch it back to degree mode. You'll likely be puzzled by the answers you get if you don't switch it back, so you'll likely figure it out that you didn't switch it back. But we don't want to take that chance. Okay, the first thing we do after your calculators are cleared, switch it back to degree mode. Okay, What does that work out to be? 0.940 times sine 18.5. 0.9971. I think you made a mistake on that one. Because we're not going to get a number that's bigger than 0.94, right? 0.29? 0.2986, Vanessa? 826? Okay, so we got the x and the y's for this now. Now let's go to actually solve this problem here, okay? Just need some space to do it. All right, so we're going to break it up into x's and y's here. Got some space here. Break it into x's and y's. Let's say pi is equal to pf for both the x and the y. There's two objects before this collision takes place. It's the centerman and the defenseman, m1 v1i plus m2 v2i. Now, these masses aren't the same, so we can't cancel. If they were the same, could we cancel? Yes, we could. Why? It's in both sides in every term, right? Now, I mean, obviously that requires it to be the same mass. Sometimes in one of these problems, it's the same mass, sometimes it's not. But unlike the kinetic energy thing, the elastic collision, we can't do that. Or sorry, where we can't cancel, here we can. All right, two objects afterwards as well. M1 is 104 kilograms, and V1I is 1.82. M2 is 97 kilograms. V2I is what? V2I is 0. So 1.82, 97 times 0 is 0. M1 is 104 again. Here's the big one right here, V1F. How many people, show of hands here, how many people prefer me to leave this diagram like this? How many people prefer me to change the diagram once I've found the x and the y to look like this? Who option number one, hands up for option number one. Okay, hands up for option number two. Okay, option number two seems to win. I mean, the upside to this is that we can see what the x and the y is right away, right, on the diagram. The downside to it is it's a little bit harder to actually visualize the problem, because obviously the player isn't going over and then down. He's going over and down at the same time. So there's trade-offs to it, right? What is the x component of the 90s? What was that object? Is this guy number one or two? This was number one, right? What is the x component of object number one's, what have I done here? I've mixed these up, right? Yeah. Mistake here, guys. M1 is the, object number one is the one that's at rest. M2 is 104. Same numbers, I guess, down here, right? But I just crossed off the wrong one. M1 is 97, and of course, V1F was what? 0.8914. And that's pretty easy to see when we look at that diagram over there now, right? 0.8914. We add to that M2, which is 104, and V2F, which is ultimately what we're going to look for again. V2F ends up being equal to what? 0.988 meters per second, and it's positive, which means goes to the right. We guessed that it was going up and to the, it wasn't much of a guess, right? We knew that it was going up and to the right. Clearly, at least half of our educated guess was right. It's going to the right. Now, let's find the y component just to make sure that it's going up as well. By the way, what exactly have I found in this diagram? Not what I'm looking for, right? I found this, right? This is what I've just got. Okay, now we need the y component of that, and then we'll combine them. So let's do that now. The y component, we're going to say the same thing, pi is equal to pf. There's a bit of a shortcut here. Okay. Sometimes I write down m1 v1i plus m2 v2i, but sometimes if I see that the total initial momentum is 0, I just skip writing the terms, just to save myself 20 seconds. Okay, 20 seconds of my life that I'll never get back. Why is it 0 on the left-hand side here? I'm sorry? Right. You've got object number 2 that's moving at 1.82 meters per second, but it's all on the x-axis. None of it's on the y-axis. And then the other object's at rest, right? Afterwards, we still have our 2 objects that we have to account for. Listen, let me ask that same question that I asked you earlier. If these were the same masses, which clearly they're not, but if they were, could we cancel them out here? Even though it doesn't appear on the left side? Yeah, if 0 appears on the left side, you're good. You can do that. Okay, M1, again, was 97. V1F. V1F is what? Take a look at your picture. Okay, we redrew it. V1F is, somebody said it? 0.29, but we're going to make it negative, yes. Negative 0.2983, we'll say. Negative because it's going down, right? Added to 104 times V2F, and V2F will equal what for the y component? 0.278 meters per second. And it's positive, which tells us, again, that our educated guess of it going up and to the right is correct. Now we want to combine them. We've got x, we've got y. 0.9, whatever that was, 0.988. This was 0.278. And of course, the resultant is this way right here. Okay, do we need to go through the process of solving this now? Or are you good with that? Good? Pythagorean theorem gives us v, and then of course the angle, always measured from the beginning, is going to be found by the inverse tan function of 0.2 over 0.9. Good? Jocelyn? Yep.
So the y that's like 0.2986.
Yep.
Would be left the background.
Yep.
That'd be like where you should left the bottom.
I'm sorry, say it again.
Like the y value is 0.27812.
Yep.
So where would that go in the diagram?
0.27812, did you say? Oh, this one, yeah. Okay, this one. Where would this be on the diagram? Well, we've redrawn it down here, right? 0.988, 0.278 as a separate diagram. But if we go back to our original diagram, 0.988 would be right here. And what was it, 0.272? Would be right here. Does that make sense? I just tend to not draw it on the original diagram. I don't do this on the original diagram either because, as I say, it starts getting really, really cluttered with a lot of numbers floating around. And for me, it's less confusing if I separate it. But whatever works for you, the best. Let's go back and take a look at question number 2 now. This one says, a 1,200 kilogram car attempting to run a red light strikes a stationary 1,350 kilogram vehicle waiting to make a turn. Skid marks show that after the collision, the 1,350 kilogram car moves this way, the other vehicle moves this way. What's the velocity of the 1,200 kilogram car before the collision? Note that this type of calculation is part of many vehicle collision investigations where charges may be pending. We have a situation in this question too, although you may not have really caught it, that there's some wording that doesn't really matter, right? We are going to see questions on our unit test, in a week or 6 days. We're going to see questions on our diploma exam in 4 months that have a half a page or a full page of context, and we have to sift through that context, boil it down to a couple of sentences that matter, a couple pieces of data that matter. And so in this question, we got a 1,200 kilogram car attempting to run a red light. Who cares? Okay, that's not our, we're not going to judge. It's not up to us to care whether this person is running a red light. We care that a 1,200 kilogram car struck a 1,350 kilogram car. Okay, my point here is that we want to ignore things that don't matter. Okay? We're going to see questions where there's a lot of stuff that doesn't matter. We want to ignore what doesn't matter. So let's draw it out here. Again, forgetting about the whole attempting to run a red light and so on. We've got a stationary 1350 kilogram car. Let's call that car number 2. Its velocity is 0 meters per second. Its mass is 1350. We don't know where car number 1 is going, but we do know that after the collision, car number 2 is going east of north. 55.2 degrees, in fact, east of north. And we do know its speed is 8.3 meters per second. We also know that after the collision, car number 1, the 1,200 kilogram car, is going at west of north, 36.8 degrees. And the speed of that car is 12.8 meters per second. Where do you think car number 1 was coming from before it hit car number 2? And remember, as you say this, as you answer this question, it's going to be a bit of an educated guess, right? We don't know exactly where it's coming from. Where do you think it's coming from? Tristan? Yeah, from down here somewhere, right? It isn't coming from up here. It's coming from down here somewhere. Mass is 1,200 kilograms. We don't know what its velocity is. Now, I've drawn this the way that most of you probably would have drawn it as well. Car number 1 is going north. Do we know that? We don't. We're guessing that it's going north, and it may in fact be north, but we don't know for sure that it's going north. Okay, so we can't assume that it is. Remember, over the last couple of days I've said it's critical that you get the diagram correct for what you know. But if we guess wrong on the other one, the one that we're trying to find, it's okay, because it's only there to help us to visualize what's going on. Let's figure out now how fast this car is moving, X and Y, and see if it is going straight north. That's the first thing we're going to do here. We get 2 funny angles, right? We don't like funny angles of any color, red or green. Okay, or blue. Yeah, we don't discriminate between funny angles. We don't like any of them. We don't like red ones or green ones. Okay, we're colorblind towards, we're red-green colorblind here towards this. We don't like any of them, so let's get rid of both of them. Let's draw the red one over here. My angle is 36.8. This is X, this is Y. Let's draw the green one over here. X, Y, this one's going to be 8.3 at an angle of 55.2. Let's get the X's and Y's for both of them here, and then we'll go back to the problem, the main part of the problem. Which side of the triangle is X, opposite adjacent or hypotenuse? Opposite, so let's use sine, good. Sine 36.8, X over 12.8. What does that equal? Seems reasonable. 7.667 meters per second. Caroline, is that what you got? Cosine 36.8 is equal to the opposite over 12.8, or sorry, the adjacent. Y ends up being equal to, what's that one? Caroline, you got that one? 10.249, thank you. Let's do the green one now. Let's say sine 55.2 equals opposite over hypotenuse. What's that one? 6.8154, thank you. Meters per second, and of course the adjacent side, which is the y component this time. Y equals Thank you. 4.7369 meters per second. All right, now for those of you who like me to redraw this, I'll do that. For those of you who don't, sorry, I'm going to do it anyways. Object number 2 is going this way, 6.8154, and then this way at 4.7369. Not drawn to a very good scale, but and the other object, number 1, is going this way and then this way. Its mass was 1,200, and it's 7.667 and 10.249. Okay, good. Now we can solve this problem like the rest of them, right? Except that we're solving for VI instead of VF, which is a little bit different, but in the end, we're still looking for still solving it the same basic way. Let's say our x components, PI equals PF. M1, can we just cross both of these off, actually? Because on our diagram, it looks like object number 2 is at rest, object number 1 is on the y-axis, so we can just cross them both off, right? Who says yes? Okay, who says no? Why can we not cross them off? Why can we not cross both of them off, anyways? Okay? No, we're not talking about crossing off masses, not canceling out masses here. Kevin? That's right. We guessed that it was going straight north, but we don't know that it's going straight north. If it's not given to you, if it's not told to you, you can't assume that it is. It's okay to write it in your diagram, because the diagram is only to visualize it, right? But we can't write it down mathematically if we're not told that's what it is. So M1 is 1,200 kilograms. We don't know. We don't know if it's got an X component or not. If it does, we're going to get a number. If it doesn't, what are we going to find V1I to be? 0. Right? This one is 0 because it's at rest. 1,200 times 6.8154 plus the other one was, how heavy was the other one? No, sorry, that was, should be 7.667, right? Negative 7.667? Is that right? Object number 1 was this one. Object number 2 is 1350. And its final velocity is 6.8154. We're going to do this here because we have some disagreement over what that is. So let's say 1,200 times negative 7.667. Let's add that to, let's use some brackets here, 1350 times 6.8154. Let's divide that by 1,200. 3.25 times 10 to the minus 4. Is it? Okay, looks like the disagreement on numbers is just a significant figure issue. Bottom line is, we're getting a number that's really small. Right? What does that tell us? Regardless of whether you get 10 to the minus 4 or 10 to the minus 5, what does that tell you about the x component of object number 1? Basically 0. Right? It's negligible, exactly. Okay, let's do the y component now. For the y component, we say M1 V1I plus M2 V2I, which we're crossing it off. So you don't even need to write that if you don't want, because we know we're crossing it off because the second object is at rest. Oops. V1F here was 10.249 because it's the y component. And V2F was also positive, but this time 4.7369. What do we get V1I to be in this case for the y component? 15.6 meters per second. All right, now we can combine the x and the y here by the Pythagorean theorem. But listen, you start trying to draw a triangle here, it's going to be not really look much like a triangle. Okay. You do the Pythagorean theorem between 0.0000 whatever and 15.6, what are you going to get? 15.6. So we guessed that it was on the y-axis. Were we right? Yes, it is on the y-axis. It's only on the y-axis because the x-axis is basically 0. So there's our answer. Had they told us that the first object, the first car, was going straight north before the collision, that would have meant all we would have had to do is the y-axis, right? Okay, in the end, we may not have caught that. We may have started doing the x-axis and found, oh, we got 0. In the end, that would have been okay. It's just that it would have been extra work, that's all. Yep.
Okay, so in this question, so one car goes 12.8 seconds one way and 8.3 seconds the other way. Well, if you calculate the momentum based off that, then momentum is being made during this collision.
No, it's not. How is momentum being made?
Okay, so if you calculate the momentum of the
X or Y?
car,
X or Y?
no, yeah, but it's not the direction it actually goes. It's not X or Y. Like, where is this X momentum coming from?
Well, remember that the law of conservation of momentum says the total momentum is conserved. Momentum is a vector. So you have to remember here that if you have a momentum at whatever those degrees were, 36.8 degrees or 55.2 degrees, we have to resolve that like we do every vector. Okay. In the end, if you've got a velocity that's at 55.2 degrees, there's an x component to it and a y component to it. If we want to compare the velocity of this to that, then really we need to compare the x and the y, okay, to the x and the y. And that's exactly what we're doing here. Look, if we want to say that momentum is conserved, we don't want to look at 12.8 times 1200 and 8.3 times 1350. We want to look at the x component of this one and compare it to the x component of this one, and the y component of this one to the y component of this one. Okay? Because momentum is a vector, we have to, just like we do with any other two-dimensional problem involving force or velocity or any other vector, we have to break it into components. Okay, right from about week 4 of Physics 20, anytime you have something that's at a funny angle, you break it into components. Okay, does that make sense? Momentum is conserved. The total momentum is conserved. Okay, but again, we can't compare 12.8 at 36.8 with 8.3 at 55.2 because of the different angles there. So what we have to compare is, that's apples to oranges. We have to compare apples to apples. We have to compare x to x and y to y. Does that make sense? We're okay there, guys? Okay, I want to have you take a look at a multiple choice question here. It's multiple choice 17, and I believe that it's on page 15 of your worksheet booklet, okay? You're going to submit this one as multiple choice number 1, please. Multiple choice number 1. We're going to take a look at this now just because we're running a little bit short of time here. Of the people that have submitted so far, 2/3 of the people have chosen C, which is the correct answer. Let's take a look at why C is the correct answer. First thing I see when I read this question are 2 funny angles. Or is it? Do we have 2 funny angles or do we have 1 funny angle? Really, it's just 1, because they both point to the same vector. So whether you're using the 60 or the 120, it doesn't really matter. Use either one. I would prefer to use the 60, because that forms a nice easy triangle, right? We can make a right angle triangle to that, unlike the 120. But in the end, the 120 will work as well. Let's get rid of that funny angle. Okay, let's go over here. We got 60 degrees here that we want to get rid of. This is x, this is y. How many people put on the hypotenuse here 1.91? How many people put 9? They're both right. Okay, they're both right. It depends upon whether you solve this question using velocity or momentum. I'm going to solve it using momentum because in the end, they've already given me m times v. Look, why would I multiply 0.168 times 15 for object A in order to get 2.52? If you use velocities, then that's what you did. You multiplied this by this, and lo and behold, you got this. They already give me that number, so let's just use that number already. The x component of this is found by the cosine function. Cosine 60 is equal to x over 1.91. That's going to equal 0.955 meters per second. And the y component is found by the sine function. I'm not sure what that one works out to be. Who's got that? 1.6541. Not meters per second, but kilograms meters per second, because we're dealing with momentum, right? Guys, remember, if you use velocity, that's okay. It's right. It's just that your numbers are going to be a little bit different than mine here. The process will be the same. Now let's go x and y components here. Okay, let's say pi is equal to pf. The initial momentum is equal to 0 because it's at rest. The final x momentum is equal to 2.52 to the right for object number 1 plus negative 0.955. That's the momentum that's to the left plus P3F. Okay, if you wanted to go M1 V1F plus M2 V2F plus M3 V3F, go ahead. Multiply those numbers together that they've already multiplied for you. It's a few extra seconds of work. It's not a big deal. Okay, but if you spot the shortcut, then maybe you can save a little bit of time. P3F works out to be what? For the x component, that is. 1.565? And that should be a negative, right? Okay, so we'll do the same thing for the y component now. The y component, once again, pi is equal to pf. The initial momentum for the y component is also 0. Hold on 2 seconds. The momentum for object number 1, y component, is 0. For number 2, it's 1.6541. And for number 3, we're going to find that. Chad, what did that work out to be?
Like canals in the front office, please.
Anybody have that already? Chad, what is it? The y component of, oh yeah, duh. Why am I taking a calculator to do that? Negative 1.6541. Now, we're going to combine these. Okay, this is 1.565. This is 1.6541. We combine those using the Pythagorean theorem. We're not going to get the final velocity. We're going to get the final momentum because we did momentum, right? That works out to be C. Now, if you did velocity, what do you got to do with this step? We're not done yet if we use velocity. We got to multiply it by mass to get momentum, right? Here's your homework for tonight, guys. Thought you'd get away with it, right, since the bell's gone. Worksheet number 4. Questions number 1 to 3. So we got a unit test next Wednesday. We got questions 1 to 3 on worksheet number 4 due for tomorrow. We're also going to have a quiz tomorrow on two-dimensional collisions, but not the funny angles. Okay, just the T-bone collisions tomorrow. Okay, 1 to 3. Yeah, that's right.